Okay, lecture solved problems for chapter 18. Take a second to read the problem. We know we have a tank that's going to be 20 liters. That's going to be 20 times 10 to the minus 3 cubic meters. We know that it's going to be at a temperature of 18 degrees Celsius. We always want to work in Kelvin, so we're going to add 273 to that and come up with 291 degrees Kelvin. We know it's got some helium in there. The mass of the helium that's going to be in the tank is going to be 4.86 times 10 to the minus 4th kilograms. And lastly, we're told what the molar mass of helium is going to be 4 grams per mole, so 4 times 10 to the minus 3 kilograms per mole. Now we can simply go ahead and calculate out how many moles are in the system, saying that the number of moles is going to be the mass of the system divided by the molar mass of the system. So that's going to be 4.86 times 10 to the minus 4th on top. That's the mass of the helium. And then 4 times 10 to the minus 3 kilograms per mole, the molar mass. And we're going to figure out that there is going to be 0.122 moles of helium in the system. Now we're asked to find in part B the pressure in the tank. Find the pressure using the ideal gas law. Pressure times volume is equal to the number of moles, the constant R, and then the temperature of the system. So we can simply rearrange this guy, divide both sides by V, and isolate pressure. So the pressure is going to be equal to 0.122 moles. That constant R is going to be 8.3145, and it's going to be joules per mole degree Kelvin. We got 291 degrees Kelvin. Divide that by our volume, 20 times 10 to the minus 3 cubic meters, and we're going to come out with 1.47 times 10 to the 4th pascals. So that's going to be the pressure in the tank. We're also asked to convert that to pascals, or from pascals to atmosphere. So we're going to take 1.47 times 10 to the 4th pascals, and we know that 1 atmosphere is going to be 1.013 times 10 to the 5th pascals. So the pascals are going to cancel each other out. We're going to get 0.145 atmosphere. So now we have our pressure in both. Now for problem number 22, it's a fairly simple one. A large organic molecule has a mass as such. It's going to be the mass of the molecule. What is the molar mass of this molecule? We know that the molar mass is going to be related to that thing called Avogadro's number. I've already written it over here to save me a little bit of time. Multiplied by the mass of the molecule. So here I'm going to have Avogadro's number, 6.02 times 10 to the 23rd. This is going to be molecules per mole. We know that it's going to have 1 mole of this guy is going to have 1.41 times 10 to the minus 21, and this is going to be kilograms per molecule. So we're going to then get our molar mass to be equal to 849 kilograms per mole, because the molecules are going to cancel each other out. Okay, take a second to read the problem. I have a container with a volume of 1.48 liters, so that's 1.48 times 10 to the minus 3rd cubic meters. It's filled with a mass of 0.226 grams, so that's 0.226 times 10 to the minus 3 kilograms. I know that it's going to be nitrogen, so the molar mass of nitrogen is going to be 28.014 times 10 to minus third, and this is going to be kilograms per mole. And I lastly know that it's going to have a RMS speed, VRMS, of 182 meters per second. So what I can do is I can relate the RMS speed to the temperature. I can say that the VRMS is going to be equal to the square root of 3RT divided by the molar mass. I can figure out what the temperature is, and then I can use the ideal gas law to solve for the pressure. So the temperature is going to be equal to the molar mass multiplied by the RMS speed squared divided by 3 times R. So the molar mass is going to be 28.014 times 10 to the minus 3 kilograms per mole. Got my RMS speed, 182 squared, divided by 3, and then I'm going to have my R, 8.314 joules per mole degree Kelvin, and I'm going to get my temperature to be 37.2 Kelvin. Now I want to write the ideal gas law. I know that I'm going to need how many moles of the substance that I have. So the number of moles is simply going to be the mass, which I know, divided by the molar mass. So 0.226 times 10 to the minus 3 kilograms of nitrogen divided by the molar mass, 28.014 times 10 to the minus 3 kilograms per mole, and I'm going to get 8.067 times 10 to the negative 3 moles. So lastly, I'm going to write my ideal gas law. PV is equal to nRT. Now I've solved for N, I've solved for T. Simply divide both sides by volume, and volume is going to cancel out for me right here, and I can say my number of moles, just calculated that, 8.06 times 10 to the minus 3. Got my value for R, 8.314 joules per mole Kelvin. Got my temperature change from earlier, 37.2 degrees Kelvin. And got my volume, 1.48 times 10 to the minus 3, and that is cubic meters. I pluck all that into my calculator and I come up with 1.69 times 10 to the 3, or 10 to the third pascals. That's going to be my pressure. Okay, last problem. Take a second to read it. I know that I have 2.5 moles of an ideal diatomic gas, and I'm going to change the temperature by 50 Kelvin, and I'm asked how much energy does that take. Now I know that for very tiny changes in heat, I'm going to be able to relate that to the number of moles multiplied by the molar heat capacity multiplied by the very small change in temperature. So I can say for a larger change in temperature, it's going to be equal to the number of moles, molar heat capacity, and then simply my change in temperature. Now for a diatomic gas, I know that I can say that the molar heat capacity is going to be 5 times R divided by 2. So for part A, the amount of heat that it takes is going to be N multiplied by 5 times R divided by 2, change in temperature. So that's going to be equal to 2.5 multiplied by 5/2 multiplied by 8.315 multiplied by my 50 Kelvin. So part A, I'm going to get about 2600 joules. For part B, it's set up the same exact way, except for the molar heat capacity is going to be different. It's going to be now 3R divided by 2. So I can write my energy is going to be equal to N times 3R divided by 2 change in temperature, and set it up the same way, 2.5 moles. Now I've got my 3/2, got my R, 8.315, and got my change in temperature, 50 degrees Kelvin, and that's going to give me about 1560 joules worth of energy.